Satya, you can start.
Welcome back to fourth session of ATAP FDP. In this session, predictivity management of EV component will be handled by Mr. Sujit Pandey and Mr. V. Kodan Raman. It's our great privilege to welcome our distinguished guest for today's session, Mr. Sujit Pandey. Mr. Sujit Pandey is currently working as a senior manager at Tata Motor Limited, where we play a key role in developing advanced data analytics and machine learning solutions for wide range of automotive applications. With over 6 years of experience in data science, he has contributed to impactful work in ICE and electric vehicle powertrains. Focusing on intelligent analytics and data driven visualization, he holds an MTech in Industrial Management from IIT Varanasi. His academic research focused on supplying a chain optimization, particularly vehicle routing problems and time series forecasting. And his work has led to a publication to two research papers in public domains. In his current role, he is actively involved in designing and developing scalable AI-driven solutions that support data-informed decision making for both internal teams and external consumers. He also holds an patent and two copyright reflecting his strong expertise in delivering end-to-end AI/ML solution. Beyond his professional commitments, he enjoys participating in hackathons, contributing to open source innovatives, and exploring emerging developments in Industrial 4.0 space. We are truly honored to have him with us today and are confident that his insight will be both inspiring and enriching. Please join me in giving a warm welcome to Mr. Sujit Pandey. And also, it's my great pleasure to introduce our guest for today, Mr. V. Kodan Raman, sir, an accomplished automotive cybersecurity engineering, currently working as a senior manager at Tata Motor, Pune. Mr. Kodandravan sir bring a strong hands-on expertise in automotive embedded cybersecurity with a specialization in secure ECU flashing, secure boot architecture, cryptographic key management, and HMA HSM, SHE integration, and UDS diagnostic. He has played a key role in implementing cybersecurity solutions aligned with ISO and SAE and UNECE. And he has conducted detailed threats analysis and risk assignments using a strict methodology. He has been instrumental in developing a secure flash mechanism using ECDSA, HSM based root of trust, and authenticated diagnostic service, ensuring a robust production for modern automotive ECUs. And his technical skills set span embedded C, Python, C, and industrial tools like Kano. Along with the deep knowledge of Astor, CryptoStack, CAN-TP, UDS, and DOIP. Mr. Kodandraman sir is also an innovator with three Indian copyrights to his credits for automation and flashing tools and has been recognized with a silver award at Tata Motors for timely and impactful project delivery. He holds an BE in Electrical and Electronical Engineering and an MTech in Power System from NIT Surat. Combining a strong academic foundation with a real world industrial impact, we are truly fortunate to have him with us today. Please join me in giving a warm welcome to Mr. V. Kodandraman sir. On behalf of the organizing committee and all participants of ATAL Faculty Development Program, I quietly invite Mr. Sujit Pandey to kindly take over the session and enlighten us with his expert talk on predictivity management for EV component. Sir, the visual stage is yours.
Thank you, Satya, for a great introduction. Sir, the session is yours, sir.
Hi everyone.
Thank
I'm truly privileged
Hi
to have
everyone.
today. Raman, you can start.
Yeah, myself Kodanda Raman. Let me know whether my screen is visible.
No, sir.
Just a second.
Okay.
Is my screen visible?
Yes, sir. Visible, sir, but not in full screen.
Just a minute.
Okay. Yes, sir. Can you minimize it? Sir?
Yeah.
Sir, can you switch on the video, sir, so that I can take one snapshot?
Uh, just a minute.
Yes, sir. One sec. Slide, sir. Slide also, sir. Full screen. Yes, sir. One second. Okay, sir. You can start. Thank you.
Yeah. Good evening, one and all. It is a great pleasure to like come back to PSNA giving a presentation like this. Uh, First of all, thanks to Mama Esmari ma'am who has coordinated well for arranging this presentation. And today we are going to talk about predictive maintenance of EV components using AI. So when it comes to automotive industry, when we see the cycle of the automotive industry, so initially the majority of the components which were there in a automobile, in a car or a bus, it was mostly mechanical components. The shift changed from mechanical to electrical components. So now, if you see, initially there were only 2 to 3 electrical components, most probably the clusters and just the instrument cluster and the infotainments. Apart from them, that majority of the components were mechanical. But now, if you see, the trend changed, the era changed, and it became electrical. And now you can say like in automotive industry, electrical and electronics plays a dominant role after the mechanical departments. So now when all these components comes into picture, electronic components comes into picture, there is a software which plays a crucial role in the functioning of these electronic items. So when software comes into picture, obviously there are software glitches, bugs, and the issues which were mechanical before now are more of electrical and software oriented. And there are also mechanical issues, and we will talk about the types of faults and categorizing it in the further sessions. So now, if we see the whole architecture of a electric vehicle, it has many components, DC-DC converter, and especially electric EV electric vehicles has even more components like a battery management system, battery coolant system, DC-DC converter, and inverters, uh, the charging port management, and ADAS sensors. And along with all this, there is another component which plays a crucial role, which is a telematics device. So, when we talk about telematics, telematics is nothing but a SIM card which is there in our mobile. Uh, a vehicle also has a SIM card kind of device, which is embedded inside a electronic control unit. We call it a TCU, telematics control unit. So what this telematics control unit does, uh, especially we are coming from a commercial vehicle background, me and Susit Pandey. So when you see it, you can say that telematic plays a very crucial role in fleet management. So what is fleet management? Uh, Tata Commercial Vehicles has a lot of trucks. A truck owner doesn't have just a single truck or 10 trucks. There are fleet managers who have hundreds of trucks or 200 more number of trucks. So they need to monitor all their uh, fleets. We say the trucks, the dealerships with remotely. They have to monitor it remotely. So for which you need a telematics device which transmits the data of the vehicle to the cloud. So now what this telematics unit does is it connects with through its internet. It connects to the server of the OEM. OEM in the sense original equipment manufacturer. The in our case it is Tata Motors. So it connects with their server and uploads all the necessary data: the vehicle speed, the fuel level, the speed, the mileage at which the vehicle is being driven, the load which is loaded on the vehicle. All these data are transmitted through the telematics control unit to the servers, and the we are providing like fleet owners the applications through which they can monitor these data. So now what happens is there are various purposes for which this telematics device can be used: for tracking the vehicle, for trip management, whether is there any fuel theft which is being happening. What you can also use it for a geofencing. This is my zone. This is my zone in which my trucks run. Is it going out of those zones? And how is the behavior of the driver? Is he doing any rash driving? Is he like maintaining proper track, and is he doing is he taking my goods safely? So all these things can be tracked using this telematics devices. And also you can use these things, use the data which is driven from the telematic device for vehicle support, like if there is any issue with the vehicle, accessing it remotely and providing solution to these vehicles. So initially, if you have seen the diagnostic of the vehicle, you say when there is issue in a vehicle, you diagnose it. You diagnose it using a protocol called UDS, and there is a communication protocol which is a embedded level protocol which is CAN. CAN over UDS is used to diagnose a vehicle. So now, initially when there were issues in the vehicle, you used to take a connector remotely, connect it to the vehicle, check what are the diagnostic trouble codes, which specifies the uh, code which specifies the supposing the sensor faults, fuel leakage, and mm, indicator not functioning, open circuit, short circuit faults. All these things will be identified, will be rectified only after the vehicle comes to the dealership. So this takes a lot of time. The vehicle has to come to the dealership, for which there is a travel, and after coming to the dealership, there is already a queue of vehicles which is there waiting for the technician. So all these things takes a more increases the downtime of the vehicle. The downtime of the vehicle in the sense the time it takes from the vehicle to come off road for any dealership for servicing, and then again go to the dealer for again go on road. So the downtime increases. Now what happens is, from diagnostic, when we are moving towards prognostic, prognostic is nothing but a predictive maintenance. You maintain the components predictively. Instead of the vehicle coming to the dealership, after that you use our tools, the technician analyzes the vehicle. Instead, you do a analysis on the data which is collected from the vehicle, readily well before, so that you can intimate the fleet owner that so and so fault is yet to occur. You can visit the nearest dealership readily, or there is a software solution for this which you can do using FOTA. FOTA is the in the sense firmware over the air. Firmware over the in the air in the sense that same telematics device can be used to update the softwares of the electronic control unit which is there in the vehicle. So now, when we move from this traditional approach to the prognostics, you have to collect lots of data from the telematics control unit. You have to do analysis on this data. And what we are creating here, for our example, we have taken a motors prognostic. Electric vehicle has a electric motor. So we are using the data to create a digital twin of that motor, digital twin of the vehicle. You have the data of the vehicle. Everything is electronics now. There are a very few amount of mechanical parts now. Using those data, you virtually create a vehicle. You virtually create a digital twin of the actual running vehicle. So now what happens is, the same way how the vehicle is running on road, there is a uh, digital twin which is running parallelly using the telematics data off road in the server. So these data are used to process the vehicle data. You create a simulated environment in which you analyze those data. You predict what is yet about to happen. So that is what AAML does, right? Like machine learnings are used for predictive maintenance. So these uh, processing of data is sometimes higher. So there is no you cannot have a high computing in the vehicle, since it is kind of overloaded. It increases the cost of the vehicle if you are having a high processing computing every vehicle. So what happens is, we do it in the edge. Edge in the sense, we do the computing in the cloud, and we intimate the outputs to the customer. So over to Sujit Pandey to take it from here. Just a minute.
Thanks, Raman. Insightful
Yeah,
presenting.
you can take it over, Sujit.
Yes. Next slide, please. As Raman mentioned, TCU is our starting point. TCU is something which captures on and off data of the real-time running vehicle, and it goes into the server. Now, when the data is already in the server, we have petabytes of data for a single vehicle running on road. If you can imagine, we have around 2,000 EV buses running on road, Tata Motors buses, and every day they are generating around 10 to 15 GBs of data. Now, if we want to prognose something, we have first to analyze all of those data points and then do some sort of analysis on it. The first part is the data analytics. What we are doing is we are just doing some pre-processing on the data. In front of you, you have uh, some graphs in terms of histograms, time series data. So we are utilizing all of these data points to make some sort of a repository, like how the data patterns are moving, what are the insights we can derive from all of them. Since we have taken motor as a component, so what all the parameters of motor we can incorporate for finding the finding the root cause of fault. Because once the fault is prognosed, the next step is to prevent it. Data analytics comprises of all these things, where we have to take the raw data, process it, find out the insights of it, and then in this process data we have to give it to the another layer which is called AIM. Next slide, please. So next slide is where we are putting our AIML approach. So what we are doing is we have say vehicle. So
Just a minute, Sajid. I will with you this.
So in the meantime, Raman comes in. I'll just explain you how it works. So as you mentioned, we are in the process of making twins of EV components. So here we are making a digital twin of motor. So it is made of two way. One way, what we do, we make some physical based model. So let us say we have our vendor which supplies motor to us. He gives us a physics based modeling. So that model we already have, that is made say in software like Simulink or say Python. Now we have to tune it from the field data. As you can see it, we are having the field data running on the roads. From there we are constantly getting significant amount of data in terms of how the vehicle is running, how the current and voltage profiles are happening, how the coolant is traveling, what is the temperature level of motor, what are the impacts of the efforts taken to reduce the temperature and everything. So basis that what we are doing is we are making a replica of real-time vehicle movement on the road. So parallelly the vehicle running on the road, and we have an off on we have a parallel digital replica running on the server. The primary purpose of it is, as soon as the fault comes into picture on the road, we should have a root cause ready. That is the part of diagnostic. And in prognosis, we have to predict few days earlier, say one day or 2 day earlier. Say this vehicle may go to fault with this much of probability, and what is the root cause behind those faults. In case someone wants to prevent that fault, what he has to do. That is all the prognosis is all for. So here what we are doing is we are collecting the vehicle data to telematics. Then we do some sort of analysis as I've already mentioned. Then we make some neural network model or any model which is having ML approach in it. Then there are certain steps like we have to design the ML approach, we have to analysis, we have to test the model, we have to run it on few vehicle, validate it, do some quality improvement in it, check it out whether the model itself needs some sort of tuning or something. Then we have to integrate those modeling with the service center, because service center are the guys who ultimately use those models. So that model's interface should be built in such a way so that they can be able to use it in a very appropriate fashion. And once all these things are done, then that model goes into the server. The purpose of AI ML approach is to make when that human understandable model, which takes input of a real-time vehicles data, and then convert the output in those insightful format, which is understandable to low-level technician, because technician is something who has to perform certain jobs. EML cannot go for every other vehicle. Technician, the model should be as good enough so that the technician should understand what he has to perform. In AI, that is our primary focus. Next slide, please, Raman. So here is that is a brief about what we are developing here. So EV powertrain components is replica we are developing, that is motor digital twin. The powertrain components real-time vehicle data they are feeding into it, and we run in the cloud so that the learnings of one vehicle can be incorporated over the other vehicles. This digital twin model keeps on running for all the vehicles running on the road, and then it keeps on training itself. And let us say some vehicle is failing repeatedly, so the model keeps on taking cognizance of the fact, and then specific specific tuning happens with respect to that specific vehicle. Now the primary purpose of it is one is vehicle prognosis, and second is the health estimation. One of the major use cases of health estimation is because there's a cost associated with the health. We purchase these components from our vendors and suppliers, and they have a say warranty or guarantee associated with it. It is very important for us to have a real-time health estimation of those products so that we can have costing done in an appropriate fashion. That is one thing. Another, let us say TML is going for some some new tender in some new city. Now you have to put some beta kind of a thing. So you have to make some drive cycle for those new cities. That you can only make when you have the past data available of some similar cities elsewhere. That way you can You can decide which motor to be put, which battery to be put, what would be the life of the battery, how much costing has to be associated. So all these parameters are needed not only for the current vehicle running, but also the future case where we are trying to expand our businesses. Lastly, this all is done through data analytics and ML approaches. The reason is, one, the components come in their own in say isolated nature. If someone is supplying a motor, so it gives a parameter of motor. Motor test data is in the form of standalone testing. Vehicle hasn't been tested by motor supplier. So although we have some physics-based model of motor, but in the running time, real time, when the vehicle runs on the road, motor may fail when the battery goes to fail, or even the failure of motor may lead to battery's failure. So whatever model is given to us, say the motor supplier or someone, that is not adequate enough for us to find out the root cause of fault. So every component is distributed whenever we develop. The primary purpose is to tune the physics-based model which we have developed, which we have achieved from the vehicle, say component supplier, through the real-time vehicle data, and that way the customization happens. At times it happens that we have to tune our model, say city-wise, say running-wise, say drive cycle-wise. Say the vehicle which has run more than 10 lakh kilometers, the model changes, and for the vehicle as compared to the vehicle which has just started its journey. So that way customization also helps us in making these twins. So the real purpose is we have telematics data, we measure the data, we make some digital twin model, we apply some algorithm to parameter optimization. Now this optimization also has a purpose behind it, because see, we have 10 15 GBs of data getting generated every other day. Now, which data is important for us, which data is not important for me, which data is important for which vehicle, it may lead to some usefulness tomorrow. It may not. It may we cannot lose it out. For how long we have to remain the data lake or something. So for that we need optimization and tuning of those parameters, so that whenever the results come out of the vehicle, if they go wrong, how we can tune it our algorithm separately again. So that way we need to have some sort of understanding. Okay, let us say 10 15 GB data is coming, so this much data I will stay in my cloud and this much I will leave it out, because that is the cost. So that way the tuning is important. Once that is done, the ultimate outputs are three. One is the diagnosis of the fault and finding the root cause. Second is the health estimation of the component, so that you can tell this component may live up to this many cycles or this many kilometers. And the last is prognosis, where you have to predict earlier this component may fail in the course of time, and in order to prevent it, what will be the way forward. Next slide, please, Raman. Now, these are the challenges of fault prognosis. One is the low data frequency. Say the reason is we are using can frame for data logging. The can frame frequency is 10 milliseconds. Now, suppose you have in buses we have say more than 1,000 signals. If every signal is coming at 10 millisecond frequency and you are supposed to put that data in the cloud, who will bear the cost? TML cannot bear it, customers cannot bear it. So we have to make a break even between both of them. Like some cost table will bear, some cost customer will bear. But in any way, only those data points has to be there which may be of use to someone. So that if the data is useful for finding root cause, put it there. If it is of no use, don't put it there. But in prognosis, you never know which data is useful today. Will it be useful tomorrow or not? Maybe it may not be. So for that, the frequency becomes very important. Second thing is the failure. In certain components, say motor and say some charger or something, they do not fail repeatedly. They fail say once or twice in their own lifetime. Now you do not have failure data. Whatever failure data you have, that is of the vehicle testing. Whatever failure data you have, that is of the component testing when it was done standalone in a lab environment, not in the vehicle environment. So even if you want to predict something, you have to rely on the complete vehicle data, but without any fault. So the vehicle running on road are not efficient vehicle. They are the vehicle which are waiting for fault to happen. So that way the modeling becomes very difficult. Third is we have fleet-based data failures. Now it's not the same vehicle is getting failed so that you have a training data, you can test it and validate it. This is how the normal course in AI approach. Here what you have, mostly the fleet happens. For every fleet, the parameter changes. Say the way driver drives it, the way the terrain, the way the vehicle is running, the way the driver is maintaining the vehicle. So for every vehicle, you have for every fleet you have say 10 vehicles which are filling repeatedly and 90 other vehicles which are running fine. But you do not have access to the who's driving those 90 vehicles. Why are those 90 vehicles during ride, whether they are maintained properly or not? Not every detail is available to us. So we cannot say that only those 10 vehicles are good because only those 10 vehicles are bad because they are poorly maintained, or they may be of say training data to you in 90 testing. That way, the segregation becomes very difficult when you do not have access to the complete picture of how the vehicles are running on the road. For this, electric vehicle powertrain technology itself is not very mature because it has been in the place for the past 5 6 years, and with each passage of time, the technology is getting matured. So the signals is coming, rate of signals, and their pattern itself is evolving. So by the time vehicle goes on the road, it becomes very difficult to find out what is going wrong, finding the root cause because technology itself is changing. We are too much dependent on our suppliers for finding the root cause and telling things. So it's not like we have made some model and it runs very smoothly. We have to depend on other vendors also. This is one of the challenge. Next point is the vendors IPR. Vendors does not divulge every details of their component. We can say but they have failed, but the reason they do not tell us, neither do they tell to anyone else. So that times that is a limitation for our modeling and everything, because we can only model where we have development, but suppliers and others where they have their own copyright, they do not divulge it. That is one of the limitation. Now next is the fault validation on field. At times what happens, we develop some model, it runs very well on the say lab testing or say in a very controlled environment running on the TML roads or something, but by the time it reaches field, certain other parameters comes all of a sudden, say the dust, water ingress, the way driver drives it, uh, overloading primarily in the trucks and all. Overloading is a major issue. So these issues do not get reported. Even if you are developing very good model, since those parameters are not taken into consideration, they do not have. Certainly the model will fail on the road. So that those parameters has to be incorporated when we are developing the model. Last is the prevention. It is very easy to predict, okay, this component may go to fail. But certainly as soon as you predict certain component is gonna fail, the next question comes is how do we prevent it? What is the least possible thing we should do so that we can prevent this failure? Now at times it becomes a mixed batch of certain actions. Say there are 10 possible actions. All of them combined may lead to failure, but not single action may lead to failure. But the technician or the vehicle owner wants to single one or two steps by which he can prevent the failure or he can postpone the failure so that he can maintain the vehicle the next day or something. So that is the algorithm has to take care of all these things also. Okay, he may postpone it, he may prevent it, he may ask you some other steps by which he can do some sort of a break even. So these are certain steps which play a very important role when we are going for developing some algorithm, not only prognosis, any algorithm for that say for having the behavior of the vehicle on the road. Next slide, please. So this is how, like I was mentioning now, we are taking a midway approach. Some certain things we take from the physics-based model, which vendor gives us, or which we have in our catalog, which we take from our suppliers' data points or something. And certain areas we incorporate our own intelligence, our own database modeling. And then in the left side, you can see we have Maxwell software, which we use for making a simulated replica of the motor. We use ANSYS and mechanical and ANSYS tool for having CFD stresses and everything, thermal stresses, high vibration, harmonics, etc. We just simulate it on the motor and figure it out, like when the vehicle runs on the road, how it behaves. These are all the this physics based part. On the right side, it is post database part. So here we take a complete vehicle based approach. So let us say motor is sitting in between, it is getting data from the battery. It is getting current from the battery. It's taking inputs from the MCU. MCU drives it, like how the motor should revolve so that adequate amount of torque and RPM is given by it in the form of output. So where the battery is sitting, what is its output to the IGBT? When the IG what are the signals which IGBT gives to the MCU as in terms of temperature, current, and voltage. Then when the motor runs it, what are the parameters which we have to incorporate, which you have to check it out on the regular basis, and ultimately how the ecosystem will behave, and ultimately which signals are there which we have a control, say temperature, say this voltage and current, and which other signals are there which we do not have a control, the temperature. So that way, the right side of the part focuses upon this database and database modeling. Combining both of them, we make some hybrid approach for making some twins. Next slide, please. So when we started this project, it was about IoT-based self-monitoring and fault detection. So the first thing was finding out what are the possible faults in motor. So it was not primarily internal and external faults. Internal, there are certain mechanical and electrical faults. So eccentricity, rotor strike, uh, bearing faults, coil and all faults are there. So there are certain mechanical faults and there are certain electrical faults. Electrical faults are of two types. One is stator fault, another is rotor fault. But this all is primarily from the engineering side, from the physics-based side. So they help us in figuring it out when the vehicle, when the motor is failing on the road, what might be the more frequent issues in it. So abnormal connections, maybe there. For that we have stator may go to fail. We have turn to ground, that may lead to failure. We have shortening of stator winding may happen. In the running time, it may be uh, it will loosen out, so the stator winding may lose, so that it will lead to some fault. Stator core related fault may happen. So these are the stator based fault. Similarly, the rotor may have some issues, the winding issues, some bearing issues, gearbox may lead to some certain failures, some sort of vibration may happen, some harmonics may happen. So that gives you a very exhaustive list of fault which may be generated when the vehicle goes on the road. What is eccentricity? What are the broken rotor? And one of the major reason of going through this literature is finding it out which all are the components which may lead to failure on the motor, so that we can take them on board also. So when we are going for uh, finding the fault in the motor, we have to take cases also on the board. We have to take suspension system also on the board, because they may lead to some vibration in the motor which may lead to the finding of the which may lead to the fault in the wiring or something. We have to take bearing teams also on the board, so because they tell us this is my life of bearing. When my bearing runs in, what are the friction level in it, which may lead to some sort of up and down harmonic motion, which may lead to some fault. We have to take into consideration BCS team also, so the cooling system, because those are the ones who take care of the temperature maintenance of the motor. In case, let us say, some temperature goes beyond a limit, that has an effect on the electric magnetic flux of the motor, and certainly it starts deteriorating. Motor will not fail that moment of time, but in the course of time, the capacity of the motor keeps on reducing, and ultimately it may lead to fail. So the for starting any project, we just start with the physics-based modeling to find a comprehensive list of faults which may come to the vehicle component, and assigning a sort of responsibility to other vehicle owners also. Say when my component goes to a failure, we need this much of help from you, this much of data from you, and by the time vehicle is running on the road, you should have take care of these many components, because ultimately combining them together gives me a clear picture of how my vehicle is behaving. Next slide, please. Next part is benchmarking. Whenever we go for some sort of technology development, we go some benchmarking how the competitors are doing, what are the new technologies in the market, and what is the modification which we can do in the current IPRs and patents already available in the market, so that we can sell it tomorrow to some other vendors or some other our the suppliers, which we can give us better product than what they are offering. So for this, we figured it out that Mahindra already has some ANSYS twin builder. They're utilizing ANSYS tool for making some physics-based twin. But later on, when we went for it, we realized that it is again the same issue. There's a isolated environment is set up for motor, and by the time we utilize it for our own vehicles, it had some little shortcomings, like it was not able to figure out the current shoots up or the voltage shoot up, because those were related issues to the battery, and we do not take battery into consideration while testing for the motor. Certainly, those faults you cannot realize in the real time. So that was from the Mahindra. There was one more, like WG Motion Fleet Management. So what they were doing is they were finding out, they're doing online monitoring and smart management there were some assets, were there electrical assets were there. So what we're doing, they were having some database. That database, they were constantly monitoring certain signals, day in and day out, finding out some sort of anomalies in it. That helps us out because certain time motor does not fail immediately. It may lead to failure after certain amount of time. This motor is a costly component, and finding out the root cause of motor failure is a very difficult issue because the number of faults occurring in motor is very less. But if the fault comes into picture, it stops the vehicle. So this paper helped us out. Okay, which all are the parameters which we need to keep on monitoring on a time series basis. Mahindra's one helped us out. Okay, how we can transform from physics-based modeling to database modeling. With all other parameters which we need to add so that we can develop some hybrid kind of a model. And the left hand helped us out. Okay, in a day-to-day basis, we have to figure out these many parameters in an anomaly kind of a fashion. Say that temperature should be within this much range, temperature should be within this much range, voltage should not go beyond this limit. We have to keep on checking whether motor fan is working or not, uh, how the BCS coolant is happening or not, whether the vehicle went for maintenance or not. So we develop some sort of a checkpoints. Okay, if these many checkpoints are correct for every vehicle on the road, say twice or thrice in a day, so that certainly the chances of failure in the coming 2-3 months are lesser. So this is how we did some benchmarking and find out which all technologies can be helpful. Next slide, please. The fault which we have taken was IGBT fault. So we have insulated gate bipolar transistors are there in the motor. They work like a switch, which aid in giving current or removing the current out of the vehicle. They generally fail because there is some short circuit and overcurrent happens on the vehicle, which may be because the DC was short or winding failure happens, and certainly it may lead to IGBT failure. And IGBT failure is a very difficult to predict one, and second, it is very difficult to it is very difficult for TML assets because it leads to stopping of the vehicle on the road. So we face these issues when our certain buses were running in Delhi and all of a sudden vehicle stopped on the road. So we have towing cost, we have opportunity cost for loss of the customers and everything. So the purpose of taking this IGBT filler was because there was a time when the number of faults for IGBT filler were coming was very high. So we were given this task to prognose it earlier so that we can prevent it. So one of the reason may be because of the overcurrent. Second can be thermal stresses. The cooling is not adequate. Switching losses are more, which will lead to the failure of IGBT. And once the IGBT failures, the motor comes to standstill. Third may be the gate drive malfunction. The voltage is not proper, resistance is not proper, so fuses are not in place. So it will lead to again a failure of IGBT, which will lead to motor standstill. And last, the aging and wear out. So we did some sort of analysis of the total life cycle of any IGBT which is positioned inside the vehicle, and finding out how that cycle is behaving with respect to the thermal cycling, mechanical cycling, because what how it is behaving when the mechanical impacts are going beyond the limit. Overloading is a major issue in buses, and it may lead to significant impact of vibration and harmonics on the motor. It may have an impact on the life of the IGBT, which will lead to failure. So these are the reason which we figured it out. Okay, this may lead to failure of IGBT. There are certain symptoms which we observed on the road, like current spikes were happening on few of the buses, not all buses, but few of the buses. But the subsequent approach is finding the root cause of the fault. It may be because of the driver, the way driver is driving. He may be taking some jerky motion or something. He may be starting the buses in a very rough fashion, which will lead to some sudden spike in the motor current. So that is one of the reasons which will lead to this failure. Second is the temperature rise. So in this case, what we figured it out was that certain buses in the summer in Delhi were facing this issue because the surrounding temperature was too high, and the BCS was not working properly because the driver hasn't maintained it properly. He didn't wait for the coolant filling in a regular basis, which didn't have an impact on emergent, like immediately didn't have any impact. Then the course of time it led to the wearing out of the IGBT, and certain and on one fine day the motor stopped. There was stalling or jerky operation. This driver tripping. Driver himself was doing some sort of engineering in the vehicle, which led to IGBT failure. There was some motor stalling or jerky operation was there because the motor was supposed to be maintained. Yes, there was one issue where the motor was supposed to be taken care, but That didn't happen because the technician himself was not aware of how it should be done, and they didn't like then lead it to some due authority for the motor moving or something. So all of once one finding the motor stop. These are certain reasons which may lead to IGBT failure and which may lead to certain symptoms. Next slide, please. So what we did was we did some auto encoding. So we have certain signals of motor. So say for CSL buses we have 100 odd signals which we give a real time value of this motor characteristic. There are certain voltage is there, temperature is there, resistance values are there, current is there. Then we have fault signals are there. There are certain faults which come and go, but they have an impact on the way motor's life is happening. There are certain alerts keep on happening, keep on coming to us. The purpose in front of us was um, uh, give a output in terms of this. The IGBT may fail after this much of time because of this reason, so that a technician on the road can go and work on that reason, and then he can prevent the motor's failure. If he can prevent IGBT's failure, the motor failure will prevent it. So that was the task given to us. So that began with doing some data analysis. We kept on checking data for the past 3 years. The first bus rolled out in 2023 in CSL, Tata Motors bus. They are currently running in 6 cities across India. And for every bus, we have to check the whole life cycle data for every motor. There are certain buses because the motors are also different in different buses. The buses which were inaugurated earlier, they had different motor, and the buses which were having inaugurated later had different buses. So that way, data size also varied. We have significant amount of data to analyze first, and uh, this make some modeling approach later, like which fault you want to predict and how much time before. There are certain buses for which time period was too less because the buses run on very less amount of time in a day. Say Srinagar buses, they run 2-3 hours a day, and there are certain buses in Delhi which run 8 hours or 9 hours a day. So that way, the continuous running also comes into picture. So all of a sudden, the data which was mainly an engineering data turned into time series based data, and there are certain parameters like who is driving the one, which depot by depot the parameters were changing, depot by depot the maintenance aspect were changing. So that way we kept on zeroing upon all those 100 more parameters of only motor and the component which have a direct impact on the motor's working, and utilizing the parameters anomaly or say uh, some sort of some sort of approaches we applied so that we can zero upon only those parameters which have a direct impact on the way IGBT failure may happen. Now, for that, we figured it out. Okay, even if the current is high, temperature is high, which all the parameters having an impact on the voltage of the motor, and this way we come across a 10 odd parameters which which can help us out in predicting the IGBT failure. There are certain components, uh, say water ingress. Water ingress is a major issue in terms of rainy season, but that water ingress is not of our use in prognosing the fault. If all of a sudden water goes inside, it leads to IGBT failure. But that we cannot predict because that is a sudden fault. Here, the sole purpose was to predict those faults which come in a time series based fashion, which start their sign in the course of which start that they are about which show that they are about to coming, and in the course of time they certainly come into picture. That way, we figured out 10 odd parameters which were directly responsible for IGBT's failure, but in a time series based fashion. Because of those parameters, the health of motor and IGBT were getting deteriorated in the course of time, and there was certain time by which the failure actually happened. If you can see in the graph right side, the autoencoder gives you a picture like this is the combination of those parameters which are having certain values beyond the threshold prior to fault. So 10 days before, the parameters started showing some sort of abnormal behavior. So this much of time was available to us to predict, okay, by the end of 10th day or 9th day, if the vehicle keeps on running the way it is running, you will lead to failure. The purpose of this was to find out which is the one which you need to change. So that way, all of those 10 parameters are responsible for us. What we did later was giving a probability of all those parameters. Out of those 10 parameters or 20 parameters, say the first two are having 80% of responsibility, and next are very lesser. But when they come in contact with those first two, they lead to failure. In the 10th day or ninth day, the one way was telling in terms of day, there are certain other parameter which was asked was number of cycle, number of kilometer. So let us say the bus runs very sporadically like Asian Nagar or something where the terrain is too difficult. So the one bus goes around, covers the area in say 3 4 hours and then it stops. So that there the target was to predict motor failure 100 kilometer in advance because that the workshop was in Srinagar and it used to cover suburb area in a day 100 kilometers. So if you're not telling before 100 kilometers, that's of no use. The bus will be out of the depot and you may not correct it properly. The second task was to convert this time series data into distance based series. What we did was we analyzed the data in terms of uh, how many kilometers after the fault is happening, what is the mean distance to failure, not mean time to failure, mean distance to failure for this sort of fault by the time the vehicle started running. That way, for distance, we came up some other parameters, say 10 odd parameters are there. That way, we came up okay if these parameters are getting controlled, this fault may not occur. In the next 100, in every 100 kilometer, we keep on checking those 10 odd parameters. Okay, this if these are taken control, so the fault will not happen. So this was the task which we did for this prognosis of IGBT failure only. Only IGBT we took care into consideration, and this way we did. One more thing we did was uh, taking care of the uh, temperature. For these sort of problems where the data rate is not very constant, you have discrete data points. You cannot rely on parameters like voltage or current because their frequency is very high, and all of a sudden spikes comes into them, and if you are not catching them properly, if not storing them properly, the analysis which you are doing may not give you the right result. At that time, temperature gives us a very good understanding, like because temperature changes in a slower fashion than current or voltage. First thing. Second, temperature is something which is dependent upon other parameters also. If your battery is heated, certainly it leads to an impact on your motor. If the charging is not done properly, if the charging is leading to some heating of the vehicle, it leads to an impact on the motor, which is not directly related to the motor signal. But for that, we need to check upon the charging signals or the battery signals. So we kept on checking temperature values even if they're showing current result, even if they're showing within those appreciable limits. Say for that we have given say 25 degrees Celsius for motor's temperature. So we keep on checking even if 25 is fine, 25 is the upper bound, or say 15 is the lower bound, and even if the temperature is say 20 for 5 days, and next is goes on 21 or 22, it may lead to a failure a day when the temperature goes beyond 25. Because by the time temperature goes beyond 25, vehicle will come to standstill. That time we cannot say we were not unaware of it. By the time temperature goes beyond 22 or 23, you have to start having some warning signal or some sort of analysis ready. That is what the prognosis is all about. So that is the third thing we did. The one was time to failure, second was distance to failure, and the third thing was checking the temperature repeatedly. Because temperature is something which gives us a real-time scenario which may lead to failure in the course of time, but which has to be taken care a very early time than the exact failure happens. Next slide, please. So these are the diagnostic approaches we employed. Real-time current voltage monitoring happened for those mean time to failure and mean distance to failure. This thing. We kept on checking the gate signal analysis, oscilloscope. Here what we did was we kept on asking the technician, like whenever a fault happens, they give us the exact amount of data. What happens when the vehicle goes to a fault? There are certain signals which come but they are not captured by TCU because the vehicle goes to a stop. Those are very relevant for us in terms of finding the root cause, in terms of having that platinum golden hour of prediction, because they tell us what are the pattern of faults which actually occurred when the motor went to a failure. What was the first thing which led to a subsequent series of faults? But at times that data is not getting captured on the TCU because vehicle goes to a stop. So the technician which was there, which first saw the vehicle, has those logs in it. So that those logs become very handy for us when we develop some modeling. That is also taken into consideration. Thermal imaging of the hotspot detection. This is very useful in terms of temperature issues. Whenever temperature goes beyond a limit, TCU gives a signal, okay, this goes beyond 25 degrees Celsius, and the vehicle stopped. But what was the impact on it? At times, it is not getting captured through TCU signals. Then thermal imaging of the component, which actually failed, gives us a count. Okay, there's a signal. Although the signal is showing that the value is beyond a limit, but it was having this impact of high temperature for how much long time? 10 days, 20 days, how much long time, and what might be the impact of it? Because at a time when we are asked to give the root cause of fault and giving the solution for a prognosis, at times we have to give accountability, like who is accountable for it. And around 10 times, 10-20% of the time, it is the driver which has to be made accountable. For those cases, the thermal imaging becomes very handy, because you have to tell the fleet owner, or someone like technician, they can tell the driver, because the way you are driving like this, temperature was going beyond a limit in the course of time, and that led to the fault. So subsequently, you have to take these many measures so that this fault can be avoided. For these many details, now the one who is directly in front of the vehicle, they give us a very accurate amount of data, which at a time TCU does not give us, because it is only giving us engineering values. And lastly, seeking switching pattern and waveform distortion. This is important from the physics point of view, because whenever IGBT failure happens, if there is something which keeps on checking on the wave flux and all is moving inside the motor, so that way we can derive prediction. Okay, the way the waveform is traveling like this, the way the modification waveform is happening, it will lead to these many failures. So these are the parameters which are beyond TCU data or beyond AI/ML based approach, but which gives us some insight about how the custom vehicle is behaving on the road, or how the one who is driving the vehicle leading, is he responsible for the vehicle failure or not. Now, the last is the preventive measures. The preventive measures, what we did was we made some sort of classification kind of thing was there, because we have these were the four metrics, these four boxes which we have to tell technicians. Okay, these all he has to take care. By the time um, he maintains the vehicle. Let us say the vehicle comes to him, he made it ready, and what he has to tell to the customer the way they should work. So the proper heat sink design and cooling. These are some design fault. We figured out some design fault in one of our vehicle. So those has to be incorporated to the design team. Okay, the next time you design, you have to take these many considerations, because that is why temperature, the coolant flow is getting hampered, and which is leading to this much of fault after this much of kilometer. So when you are simulating your component, take this into consideration. So this is one of the preventive measures. The junction temperature we have to maintain, because uh, this is where the current shoots up happens. Because of this, impact on the resistance, something that junction temperature was going beyond the limit. So by the time next time when we are going for electric wiring or wiring harness something, those have taken care, because of certain abnormalities in the way we are driving and we design the wiring harness. This temperature goes beyond the limit when the driver drives like this, or when the all of a sudden coolant stops flowing. So it has to behave in an appropriate fashion. Third was soft start mechanism and control switching. Like we have touched the driver the way you are driving like this. So because of this issue is happening. So you drove like this, so that you can prevent these failure. The last is the gate drivers and protective circuit. That is one we give to the IGBT vendor. Okay, because in our vehicle the overloading is a major issue. These faults are coming repeatedly. We have told other vendors also to work upon them. You also work on it. Give me this much of configuration of the IGBT, so that it may not lead to failure tomorrow. So these are certain preventive measures which was taken. So overall, the whole purpose of telling you this is how the major steps which take into consideration. Digital twin is all about all the faults which may happen on the motor. All out of them, we took this IGBT failure, because this was more frequent. Once upon a time, this was more frequent. Because of these preventive measures, we are able to control it out. But there were certain cases which we could tell in advance to the TML workshop people or TML technicians. Okay, this motor may fail. Ask the driver to come to the workshop, do this much of thing, fill the coolant, or check the wiring harness first, check the IGBT, they have been worn out, and they may need to fill in the motor in the coming periods of time, because that way we could save the motor. IGBT failure should not lead to the motor failure. So this is how the twin helped us out in finding, prognosing the fault and preventing it out in the course of time. Now it's next slide, right? And now, yes. So thanks a lot everyone. This was the whole about how we are utilizing those data and physics combined approach on a real-time basis in our buses, and what are the benefits it is driving to us, what are the technologies which are employing, and ultimately how they are leading to the customer centricity for both a technician also and driver who is driving the vehicle. Thank you. If you have any question, you can ask.
Hello.
Hi, yes, yes, sir.
Uh, the battery-driven vehicles only have a problem of speed. Some limitation is there, and they cannot go. I mean, distance-wise also some limitation is there. Is it not? So means after traveling sometime the battery gets discharged. That is the problem.
Yes,
So
range.
long charging time is also there. No, these are the two lacunas.
Yes, yes. So range is a major issue in electric vehicle.
Mm.
It takes say at least 30 minutes to get the complete charging. Say we have Nexon and other products on the road. They take 30 minutes for getting charged. But that is, I believe we have more engineering challenges. We are working upon lithium-ion batteries currently we are using. We are working upon sodium-ion batteries, aluminum-ion batteries are there in the pipeline. We're working some way on lithium carbide anode kind of a thing, which may lead to more this battery capacity, more ion discharge potential, so that the sort of fast charging which is already there, but it takes around 30 minutes, that can be that can be more
So
speed up. Mhm.
another question is, for how many what are the chances of battery getting burst?
Mhm. So there are, I must say there are more number of chances of getting burst. The primary reason is thermal management of battery has to be very adequate. We have taken we have ARAI standards in terms of it, for which every battery OEMs has to follow. So that I believe everyone follows, but the chances of battery burst happens when the way you are driving is not adequate. See, battery driving is different than ice vehicle driving. If you keep on having your foot on the act pedal repeatedly, it keeps on driving the current. But if the current is not utilized properly in the powertrain, certainly it would lead to thermal stresses on the thermal management system across the battery. One thing. Second, cells. All the cells do not have access to the coolant adequately. That cannot happen because you have cell stack kind of a cell. So one way, if you're not repeatedly, if you're driving electric vehicle in an inappropriate fashion, it will lead to some bursting. We have seen cases where the battery firing happened in a very extreme heat up environment, say Jaisalmer or somewhere, where the external temperature goes beyond a limit, so that the coolant itself could not give the adequate coolant power, because coolant temperature himself itself goes beyond a limit. So that those are the inputs which came to us, and we switched from one coolant to another coolant with high specific capacity or something. So there are chances of battery. I believe there are chances of battery heating up, battery catching a fire. In the recent, we have seen one Mahindra vehicle got fired up. But yes, for that only we are going for prognosis and all, because battery firing is something we call thermal runaway is a case where a current goes beyond a limit and all of a sudden battery catches fire. But in any of the cases, there is a time of 5-10 seconds available, and that way we can save at least the person sitting inside the vehicle. This is where the prognosis comes very handy. But for every vehicle, yes, there are chances of battery taking fire.
Right, sir. Right, sir. Thank you, sir. Thank you.
Thank you.
Hello, sir. Sir,
Hi.
Selection of switching frequency for IGBT, it should be some 5 kilohertz or 10 kilohertz. How to identify the suitable range of switching frequencies?
I believe that is the design decisions. Uh, Whenever you design the whole component and motor and all, that times these decisions are taken care. Depends upon the way which motor we are using, the way our drive cycle is all about. So those are the design decisions which you take care when the vehicle components are getting designed. For this much of torque you're preparing, so this much will be the frequency. This much only I can tell. Like there are certain parameters I cannot reveal, but this much of I can tell. Like when the new vehicle is designed, what are the requirements out of the vehicle in terms of torque, current, and torque and RPM, and what is the maximum power you can decide. That will IGP decide.
Okay, sir. Thank you.
Participants, any other queries? Okay, if there is no queries, shall we wind up, sir?
Okay. Thanks a lot for your lovely patience.
Thank you, sir. Thank you so much for your informative session. Suchit Pandit, sir, as well as Kothana Raman, sir. Thank you so much, sir.
Thank you. Thanks a lot.
Thank you. Thanks a lot.
Thank you, sir. Participants, the feedback link has been posted in chat box. Just fill in the feedback form for the session. Thank you.
Thank you.
Thank you, sir.
Thank you. Thanks a lot.
Participant, the feedback form will be posted in chat box. Kindly fill the feedback form for today's session. Session 4.